Okay, so, we have started looking at the resolution method for first order logic, and to do that we were looking at how to convert a formula into clause form. So, let us look at an example, and let us say this is the formula given to us that for all z and let us say this is we want to show that this formula is unsatisfiable. Let us not worry about how we got it, but to show that it is unsatisfiable we want to first convert it into clause form and then use the resolution method to show whether that we can derive the null clause essentially. So, if you remember the steps, then the first thing that we do is we find that there is a free variable here y. So, we add a quantifier here, there exists a y, that is the first step. So, we now have no free variables left and we need to now convert this into clause form essentially. So, the first step is to remove the quantifiers, sorry, remove the connectives. So, we get there exists y for all z. Now, this equivalence we will break it up into two parts, which is by implication one both ways. So, one side we will say that p z y implies not this, and the other is the other way around, which is that so we handle this one now. Next we handle this and this here. So, we get that is the first part, and the second part is that. So, because we are removing the knot, this will go away. This whole thing or p z y and an appropriate number of brackets, I think. Then we push the knot inside, and that is only in the left hand side. So, let me rewrite that part. So, when I push the not inside, I will do both the things in one step. I will push it across the quantifier and then I will push it into that AND. So, that AND will become an OR and the quantifier will become a universal quantifier. And the right hand side remains the same. So, I will not copy it here. Then we need to eliminate the universal quantifiers, the existential quantifiers. There exists y and there exists x. So, in this case, in the first case where there exists y, there exists is basically is not in the scope of any universal quantifier. So, we will be left only with the universal quantifier, which is for all z, and this formula where there was y, we will replace with some Skolem function, let us call it sk1, Skolem constant, and the remaining part of this formula will remain the same. So, this thing, whereas on the AND side, this existential variable x is in the scope of the universal variable z essentially. So, it must become a function of z. So, this will become p z. So, let us call this Coulomb function also some sk function. So, let us say sk2 of z and p sk 2 of z comma z and the whole thing with p z y. So, we have eliminated the existential quantifier, after which we can bring the universal quantifier, this universal quantifier we can bring it out here, and so we do not have any quantifiers inside, and inside we have only and, or, and not. So, all we need to do is to distribute next. So, this for all x will come here. So, once we distribute, we will get for all x for all z. Now, the first of those conjuncts is already in clause form. So, we do not really need to do much, but let me just write it again. But the second part we need to distribute the AND over the OR. So, we get p z sk2 of z or this p z y. So, this is becomes another clause, and p sk2 of z comma z or p z y. This becomes the third clause. So, we are left with 3 clauses. Now, we can throw away the quantifier symbols and we can rename the variables in each of those 3 clauses. So, which are the variables which is common, which is z. So, let us say that this is clause 1 and clause 2 and clause 3. So, we can rewrite the 3 clauses as a set. So, the first clause is this one, not p z, let us call it z1 sk1 comma not p z1 x1 comma not p x1 comma z1. We just call them with a subscript 1 or suffix 1 to say that it is a first clause. Likewise, the second clause would be p z 2, let us call it, and sk 2 of z 2 comma p of z 2 comma y 2, and the third clause in a similar fashion is p of sk 2. The function will remain the same, but its argument has become different, z 3 comma z 3 comma p z 3 comma y 3. So, we started with this formula which was in first order logic, and we have ended up with a set of 3 clauses which use the universally quantified variables z 1, x 1, y 1, no, not y 1, y 2 and y 3 essentially. So, this illustrates how one can convert it into clause form essentially. Now, let us go back to the resolution rule. The resolution rule says as follows, that if you have 2 clauses, C 1 is made up of some formulas, let us call it a set S union set let us call it P. So, by this I mean that or let me rewrite it. And by this mean a set of formulas using predicate is just an informal semi formal way of trying to describe it, and we have another clause C 2 which is R 1 R 2 and a set of formulas which are of the type not P in a similar fashion. And from this you will derive the set R 1 R 2 union S 1 S n if all P in this if all P's can be unified with theta, and then we must apply this theta to this. So, it is basically similar to what we did in propositional logic, that we will remove certain instances of a formula, and then the remaining we will keep essentially. So, let me just take an example from the last this thing that we just showed. So, we derive these 3 clauses. So, let me look at one of them. So, not P Z1 SK1, not P Z1 X1, the same I am just rewriting it, not P X1 Z1, that was clause 1, and the second clause was P Z2 SK2 of Z2 P Z2 Y2. So, from this what can we do? So, supposing we were to take the following substitution, x1 becomes equal to sk1, that is allowed because it is a constant. Then z1 is also sk1, so our goal is that because this z1 and this x1 and this sk1 we have want to unify, they will all become the same. So, all this in the first clause the 3 parts will become identical. So, they will all become not P sk1 sk1. So, if you look at this z1 will get replaced by sk1, this z1 also will replace epsilon and so on essentially. So, the goal is to convert all 3 into that, and then from the second clause supposing we choose this z2 is also sk1, then all these underlined things will become sk1, and this set of 3 clauses will cancel this set, this one clause, one literal from the second clause, and what we will be left with only the second, this one clause which will say P sk1, because we have substituted that in sk2 and z2 is sk1. So, this comes from here and this whole thing comes from here. So, it is similar to what we did in propositional logic, that we cancel positive and negative clauses, but for the sake of generality we have to state this rule in a more general form, in the sense that when we did propositional resolution we would cancel exactly one positive literal and one negative literal from the 2 clauses. In the case of first order logic, as this example shows, from the first clause all 3 vanish, from the second clause one of the 2 vanishes, and we are left with only one essentially. And in general, it could apply to a whole set like this essentially. So, let us see that the resolution method is in fact a generalization of both forward chaining and backward chaining. So, just let us take our favorite example, which is this Socratic example. We said that man Socrates and in implicit quantifier form man x implies mortal x. You want to show that mortal Socrates. That is the example that we started off with. And this example in forward chaining, how does it work? That you have essentially match left hand side. So, you have man x implies mortal x, and then you have man Socrates. So, you unify this and you produce and infer mortal Socrates. This was in forward chaining. In backward chaining, we said from goal mortal Socrates and rule man x implies mortal x, you infer the goal man Socrates, and this matches the fact. Now, let us just rewrite this whole thing in clause form. So, we have man Socrates, and the other clause we will have is not man x or mortal x. This is this clause I have rewritten in a clause form, that is all. Now, you can see that first of all forward chaining is a straightforward instance here of resolution. You can resolve this and you will get mortal Socrates. So, forward chaining is just a way of just one particular way of doing resolution essentially. What I have applied on the right hand side in blue is a resolution rule, and I have come up with something which is equivalent to this. So, this is equal to this. So, I have not done refutation here, I have just shown that you can derive mortal Socrates, but in refutation you add this, the negation of the goal, you add this, and you add this to a set of clauses that you already have, which is, so let me just take the rule part here, man x or mortal x. Again I can apply resolution to this and I will get not man x. So, if you look at this part and this part, you can see that something very identical is happening. Only if you can think of the goal as a negation essentially. So, if in the left hand side instead of goal, which is a kind of a marker for saying that it is a goal, I replace it with a negation sign. So, which is what I have done, I have replaced this goal with this negation sign here, and what I get is a new formula which has a negation sign, which I can always interpret as a goal essentially. So, you can see that with by adding the goal with a negation sign, I am essentially doing what backward chaining was trying to do essentially. The same inference I am making, that from show that Socrates is mortal and the rule that all men are mortal, I reduce it to a goal called show that Socrates is a man essentially. Okay, so somebody should have pointed this out. This is Socrates. So, the sub goal that I have to apply the substitution x equal to theta. So, I have reduced it to this goal. So, this negation is a little bit like show, like goal, saying that it is a goal or not essentially. And to this, if I add the real fact which is man Socrates, then I said here that this matches a fact, but you can see that it amounts to saying that I can take that fact and this goal. If you think of this not man Socrates as a goal, you match it, and what you really get is a null clause essentially. So, this matching fact is kind of equivalent to this essentially. So, I have three clauses. I have Socrates is a man as a clause, I have all men are mortal as a clause, and then by taking the negation of the goal, which is that not mortal Socrates, I get a third clause. If I, as you can see on the top, if I resolve man Socrates with the rule, then it is like doing forward chaining. If I resolve not mortal Socrates with the same rule, it is like doing backward chaining. So, backward chaining, you are doing the same thing, you are chaining with the same rule, you are going from goal to sub goal, or you are going from fact to new fact essentially. But essentially what we can see, if you think about this a little bit, is that when you are doing resolution, you are subsuming both those activities, and really it really depends upon what is the two clauses that you pick to resolve essentially. If you pick the first two, it is like forward chaining, if you pick the second and third, it is like backward chaining essentially. For the sake of completeness, and this we will come to in the next class, it was shown by Alan Robinson, who invented this method in 1965, that the method is complete if you want to show that some formula is unsatisfiable. We have just seen an example, we saw those two examples of those blocks, green blocks, and we said that we can't do it with forward chaining and backward chaining, and then we, at least one of the examples we showed that we can do it with resolution method, and the second example hopefully you will do as an exercise and show that it can be done by the resolution method. So, we saw that something that we could not do with forward chaining and backward chaining, we could do with resolution, and in fact Robinson formally proved that the resolution method is complete whenever you want to derive the null clause essentially, which means that if you start with a set of formulas, or if you start with a formula which is unsatisfiable, then you can derive the, or you can always derive the null clause. So, in this example it shows that if you have these three clauses, that Socrates is a man and all men are mortal, and Socrates is not mortal, which is the third clause that we add, which is a negation of the goal, then these three clauses, this one, and this one, these are unsatisfiable. And we have gone through this argument. Why do we call them they are unsatisfiable? Because we can derive the null clause essentially. I can manage to write this. Okay, so we have seen an introduction to the resolution method. In the next class, we will try to look at some of the intricacies of using the resolution method, and we will talk about complexity a little bit, and then try to see whether how can we make things more efficient essentially.